Firstly, I'd like to thank you for taking the time to attend this talk and to the organizers at UXDX for the invitation to speak. I'm Amanda Chu, VP of Product at Horizon Quantum, where we're building a new generation of programming tools to simplify and expedite the process of developing software for quantum computers. I've been in the tech industry working on product and software developer tools, and I've always enjoyed building tools for software developers. My background is in mathematics and computer science, and now working on developer tools for quantum computing at Horizon Quantum reflects a commitment to making quantum computers accessible to anyone who can program today. Today, I'll share a little about how we've approached and applied product thinking to quantum computing at Horizon Quantum. In particular, to abstract away quantum computing and quantum mechanics in a way that enables users to write quantum applications from classical code without any knowledge of quantum computing. And the reason we care about this is because computers and computing has changed the world. Part of it has been hardware, and part of it is also software. In particular, the software developer tools that enable domain experts to make use of computers to solve hard problems. And what it means to compute today is starting to change. Quantum computing is fundamentally a new form of computation. It's the study of computers using quantum mechanics, which is a discipline of physics that looks at particles and their interactions at a very small scale. So we're talking about atomic and subatomic particles like electrons, nuclear spins, and photons. And so the use of quantum mechanics opens up concepts and techniques such as superposition and entanglement that we can draw on to enable computation and quantum information processing. When processing information, quantum computers can draw on the interactions between different computational pathways at the same time, rather than traversing a single pathway like that in a conventional computer. And that's the key to its high and large computational power that can lead to dramatic performance gains. And so if you're working in product in such an industry or in a deep tech industry, there are some implications on how you build product. For example, what are the unique aspects of quantum computing and how should this impact your product roadmap, your strategy, and how do you balance both short-term and long-term planning? Regarding the audiences or the users, who are these target audience for quantum computing products, both today and in the future? And how does the choice of audience impact the way you build your product? For use cases, what are some early use cases for quantum computing? And what does a minimal viable product, the MVP, how does that look like? And what should we build to anchor product development on real user needs that can both deliver value today to users and also gather user feedback to iterate and build for the future? And lastly, on metrics, how do you measure success or product market fit when traditional metrics may not be as relevant in an advanced and early stage field such as quantum computing? Quantum computing represents a fundamental shift in computing technology. And each time we've seen such technological shifts, it has always and led to tremendous value creation. And so the quantum computing market is forecasted to achieve around 80 to 170 billion by 2040 in total annual revenue creation for end users. So in the present, an attempt to find product market fit requires an understanding of the users, their needs, their work to be done, and their use cases. So in today's session, we'll learn about an approach and attempt to identify the users when the technology is still nascent, how to uncover the users' unknown needs, observe their work, and find the present and future use cases. Of course, we don't have all the answers yet, but hopefully by sharing an approach, it might be useful in applying these lessons to your own product domains. Typically, we've seen how users adopt technology in conventional computing, as you can see in this graph. But for deep tech, how are the early users different from that in conventional computing? We realized that the early users might come even before the innovators that you see in this graph or in this diagram here. So we should consider users involved in research or academia, people who can understand and see the value in the technology. While building for the present, we should also consider for long-term users. And for quantum computing to reach mass adoption, it still has to be accessible to majority of users. For example, to domain experts who have their own use cases in their own industries today, and we have to find a way for the product to be incorporated in their existing workflow. To reach mass adoption, the classical code that developers write today, written for conventional computers, will also have to be eventually ported over to quantum computers. So although quantum computing, it holds the potential to address some of the world's most challenging computational problems, for a majority of users, it's still hard to harness the power of quantum computers effectively. And we see a couple of barriers for the users. Firstly, quantum computing is extremely non-intuitive, and it makes it difficult to develop new quantum algorithms. This is because quantum algorithms, or building quantum algorithms, it relies on the interference between the different branches of the wave function in a way that it's outside the realm of our daily day-to-day experience. And this presents a steep learning curve because it takes a lot of effort and experience before we're actually able to make some decent progress there. Next, there is a diverse range of hardware architectures, and they are imperfect or noisy. We haven't reached fault-tolerant quantum computing yet. So to get the most out of today's quantum computers, you will need to write code that's tailored to the hardware, which generally means it won't work well on another piece of hardware, on another piece of architecture. So the code is less portable from one hardware architecture to another. Lastly, our current programming languages and programming tools lack abstraction, and they're still in its primitive stages. So you're piecing together a quantum circuit together, logic gate by logic gate. And you can imagine it's quite a daunting task to write a complex piece of quantum software in this manner of detail if you use assembly language or something that's even lower level. So knowing the limitations or the barriers for users in programming on quantum computers, how we approached finding our early users was in terms of three categories. The first was their expertise in quantum computing. Next, the impact, which means how likely and quickly would the user see the impact of our product with minimal explanation or minimal handholding. Next, it's also on the reach of how widespread are these potential users in industry or in the world today, so that we can build our product in a way that enables it to scale to a majority of users. For these three categories, we've also considered the potential of the user to adopt a new product from an early to long-term scale. And this brings us to three different types of user groups. Firstly, quantum experts who have high expertise in quantum computing, and they're able to see the value of any software or hardware very quickly. Next, there are programmers, developers that are very widespread in their reach, or there's a majority of programmers today and domain experts in the world today. And you can see the relative position of each user group on a scale for each category. For each of these user groups, let's also consider their potential use cases according to their quantum expertise. So the current applications of quantum computers that we most often hear about today are those in pharmaceuticals. For example, think about molecular simulations, and also in banking. And an example of such application is portfolio optimization. However, we think there are way more possibilities waiting for us to discover, because at its core, quantum computers are a type of high-performance computers. So there could be an impact on all industries that make use of high-performance computing. And such examples of industries and use cases are the aerospace industry for problems in computational fluid dynamics, the semiconductor industry for complex electromagnetic simulations, and oil and gas for geophysical calculations. So the question for us in product is how to make these use cases applicable to each user in their own domain according to their level of quantum expertise. As quantum computing is still a nascent field, we have less examples and references for building products in this segment of deep tech. That being said, we can learn many lessons from the history of classical computing in the early 1940s to 2000s as to which products prevailed as compared to their competitors and the reasons for their successes and their failures for both the software and hardware. It's also interesting that we can see similar patterns in the development of algorithms for both the classical and quantum computing fields. So with this in mind, we've built a product, or the way we approach product development in deep tech at Horizon Quantum is we imagine if things were different. We imagine that you could program a quantum computer in the same way that you can program a conventional computer today. This means anyone who can program, if you're a domain expert or a developer, you could write code that is fast and efficient on a conventional computer and is automatically accelerated on quantum hardware. What if you could also abstract away the quantum mechanics and give the domain experts in different industries the tools and capabilities to build quantum enhanced programs without needing to understand the underlying quantum mechanics or model, and they are able to write code that works well on both the classical and quantum hardware. And what this results in at Horizon Quantum is we are building products that covers these abstraction layer. We are building a complete development toolchain that we've exposed to the user at varying levels of abstraction that helps to expedite and simplify the process of developing software for quantum computers for both programmers and quantum experts. At a higher level, you can see in the first layer of the graph of this diagram here, we envision users being able to write in their classical programming languages like Python or C, and then we'll automatically break down that program structure into its basic components and automatically generate a quantum algorithm for their classical program. At the lower levels then, we then compile this program down to the quantum hardware, all the while being aware of its topology and the constraints and limitations of the hardware. And then deploy this quantum program as an API so that the user can run it in their current workflow and run the API in their current program or wherever they are working. And if they run the program, they get the results of their compiled quantum program. So our product is called Triple Alpha, where you can write code in classical programming languages, and you can program in a similar way as conventional software engineering. So in this image here, you can write subroutines from C and C++, and our compiler will automatically construct a quantum circuit directly from the functions written in these classical languages. In modern day software engineering, you also will program with flow control elements like for loops, if statements, while loops, and so on. So for us, our languages are also Turing complete, which enables you to leverage on flow control to overcome the limitations of circuit-based quantum computation. You can also quantify the resources for your quantum program and compile and optimize your quantum programs for any quantum computers of different modalities, because our compiler will map it to the native operations of any target hardware. Lastly, you can get the results of your compiled quantum program via an API that you can embed in a wider program. Beyond this, there have also been an accelerated and tremendous progress on quantum hardware in the past recent months. And with that, it's also important to adapt to the advancements in research and in deep tech. So what we realized that we wanted to establish a quantum hardware testbed in our Singapore office to be able to co-develop both quantum hardware and software. And our testbed has the capacity to host up to 3 quantum computers, and we will have our first quantum computer up and running by early next year in our Singapore office. We're the first quantum software company in the world to do so, and we see this tight integration between both the hardware and software as critical to getting to useful quantum computing. This brings me to the end of my talk for an approach to applying product thinking to a deep tech region and segments such as quantum computing. Thanks for taking the time to attend this talk today.